Good morning, good day, good afternoon. Welcome back to iC-Haus webinar series. Today we'll have a webinar about high-resolution absolute magnetic position encoders. And I'm joined today by Mr. Magnus Meyer and Mr. Patrick Stahl. And before I pass over the word to Magnus, I just want to give you a quick instruction on how to use the webinar tool. So you have a control panel. If you click on the red arrow or the red button with the white arrow, you will be able to see the functions of the control panel. If you click further down, you will have a questions section. In this question section, you can raise your questions to the team. They will be played to the webinar team here, and I will get them to me so I can read it out at the end of the session. Please place as many questions as you have, and should time not permit for us here on the panel to respond to your questions, we will absolutely respond to your questions via email and get back to you with the answers we will give you. We also have two screens. The top side shows the actual presenter, and the bottom one shows the actual presentation. In the middle, you will have a cursor which you can move up and down, so you can size up the screen you want to see in a larger mode. But please be aware when you use this function, don't go all the way up, all the way down. You might risk to lose one of the screens, so just be careful when you move that up and down. So without further notice, I will pass on the word to Magnus. So Magnus, tell me about what you will present today, because we have had the MU series in the market for a while, and I'm sure you have something new to tell us today.
Okay, thank you, Henrik. And yes, that's right. So the iC-MU series is very well known in the market. So that means we have customers who use them already for many years, also in series production. But we also have new customers who would like to get more information about it. So hello and welcome. My name is Magnus Meyer, and I'm a sales and application engineer at iC-Haus. And together with my colleague Patrick Stahl, we're doing application support for encoder ICs and especially for the iC-MU series. So let's see what is waiting for us now. We divided this webinar into two parts. So in part one is more related to the newcomers. I will give you an introduction about the iC-MU series. We will see how can we calculate an absolute position with the no-news principle. We will dive into the chip and see how the analog and the digital part is built up, which interface options we have, and then I will summarize all the features up and we see some typical applications. And then without a break, because this webinar is around 45 minutes, we go to part two, and Patrick will show you how easy it is to set up with our evaluation kit a demo system in a lab environment. So he will do some mechanical setup, and we will show you something new. This is the new calibration, and Patrick will explain how it works because we have done some improvements here. He will also show you some tips and tricks which we know from the application support, and he will show you a special function of the iC-MU. And then I will end up this webinar with an overview of magnetic code wheels and linear tapes. And then we are ready for your questions. So let's get started. When we talk about the iC-MU series, we talk about three different chips. It's the iC-MU, the iC-MU 150, and the iC-MU 200. And the main difference is the pole pitch. And we will later see why we have these three different ICs. So we can scan magnetic code wheels, for example, in an axial rotary application, or in radial rotary, which you can see here on the screen, or we can use them in linear applications with scanning a linear tape. We have two Hall sensor arrays on the chip. One we call the master track, and the other we call the no-news track. And with these two Hall sensor arrays, we can scan two magnetic tracks. You can see it here on these example pictures, and these are two incremental tracks. But how can we calculate an absolute position from two incremental tracks? This is done with the no-news principle. And I have brought here or simplified the no-news principle a little bit with this graphic here. I have plotted here a master track with 6 periods because then it's easier to understand it. And what we are doing with an interpolation is we do a digitalization of each pole pair, and then we get an absolute information, but only within one pole pair. So this information repeats 6 times. And for example, when we are at a position like 60 degrees, I've plotted here a dot, then this can happen 6 times on a magnetic code wheel, for example. And the question is now, how can we distinguish which period we are? And therefore, we have the nonius track. And the nonius track is always 1 period less than the master track. So in our example here, it's 5 periods. And for better visualization, I divided one pole pair of the nonius track into 6 parts because we have 6 master periods. And I've plotted here some numbers. And then when you look at the first period of the master track, I have a vertical line and it goes direct into section number 1. And then we go into section number 6, 5, 4, 3, and 2. So by reading the master and the nonius track simultaneously, we can calculate the absolute position or in which period of the master track we are. And then the absolute position is built up from a master period counter and an interpolation of the master track. So this means the accuracy of the system is related to the accuracy of the master track. When you look at this vertical line, you see maybe it's not perfectly in the middle of this section number 1, for example, which I have plotted here. This means the master and the nonius track stands in relation to each other, and due to mechanical misalignment, it is not ideal perfectly in a phase, and therefore we have the nonius calibration. And for visualization, the nonius calibration is something who shifts the nonius track a little bit to align it to the master track in a perfect way. And therefore, we have the nonius calibration with our GUI software. Patrick will later show you how this works. So let's see how the analog part is done. And so we have the Hall sensors scanning the magnet, and these sensors have 2 amplification stages, a coarse gain and a fine gain. And both are controlled by automatic gain control, and you simply have to switch on these and then you are fine. And then also due to some mechanical tolerances which we allowed for mounting, the signals are not perfectly. And so we can adjust them in the difference amplitude. We can correct the phase between sine and cosine, or adding an offset in sine or cosine. And this is also done by an automatic calibration via our GUI software. So after this analog signal conditioning, we will have perfect sine-cosine signals, and these signals going into an interpolation circuit. So we called it sine to digital converter because we feed in sine-cosine and we get out a digital angle information. So we have 2 of these interpolations within the iC-MU series, one for the master and one for the nonius track. And then we have a filtering afterwards to getting a 14-bit resolution of each track. So, and for the master track, we have the fine resolution. And then the nonius track, there is a nonius calculation and synchronization using the master and the nonius information to get the correct period count value. And then we have an optional multi-turn, which we can read in via the SSI interface. And this I would call a revolution counter. And these 3 parts of a position word is synchronized, and then we have the internal absolute position. And this absolute position then goes to several interfaces. For example, I plotted here in blue and red this multi-purpose I/O ports. It's port A and port B. And then you can configure which interface you like to have on each port. So for example, port A has an SPI, BIS, or SSI interface, and port B has the digital outputs ABZ, UVW, or the sine-cosine signals of master or nonius track. And for example, when you like to have the UVW signal on port B, you have the option to configure ABZ on port A to have both signals for motor commutation. All these configuration and calibration data are stored in an EEPROM, and this is connected via this I2C bus. And you have the option to connect additional devices to this bus, for example, a temperature sensor, and then you can read out the temperature value through the iC-MU, for example, over a BIS or SPI interface. Or we can have a link to the IC-PVL, which is our multi-turn chip, and then we can configure also this chip. The multi-turn interface, as the name says, you can read in a multi-turn value, or we can do a cascading of 2 iC-MU to scan 3-track magnetic targets to expand the measurement range or distance. So summarize these up. The iC-MU, when we talk about iC-MU, we have 3 different chips and 3 different pole pairs, pole pitches. And we have the opportunity to select 3 different non-use systems. So my example was with 6.5, but the iC-MU can detect 16.15 or a 32.31 or a 64.63 non-use system. So with this combination of the different pole pitches and the different non-use systems, we can allow to have different diameters, for example, for rotary magnetic targets. And I draw here a table from our product flyer. And for example, you can see when we start with the iC-MU, we have a largest inner diameter of 3 mm with the smallest size of magnetic code wheel. And we end up with MU200 with 70 mm. And of course, when we talk about different diameters for rotary magnetic code wheels, when we go to linear, we have also different absolute measurement lengths. We have a 19-bit position resolution internally, for example, with systems with a non-use system of 32 pole pairs. The incremental part or the incremental output ABZ, there is also a flex count option possible, so you can select every interpolation factor between 1 and 65,000. Or you can select a resolution for UVW signals from 1 to 16 pole pairs. We talked already about the interfaces, BIS, SPI, SSE, and sine cosine, and the multi-turn interface. So, and to see some typical application, of course, the iC-MU fits very well in robotics. So when you have a robotic joint, you will always have a motor and a gearbox. And iC-MU can use on both sides. So for example, at the motor side, doing motor commutation, and you can use it for regulation, the speed, and so on, velocity. And then after the gearbox, you can use an iC-MU as an absolute encoder, getting this absolute information and seeing, for example, where the robot arm stands. We talked already a little bit about motor feedback, so you can use it for servo motors, BLDC motors, or stepper motors. And when you extend the system, for example, with a PVL, scanning the same magnetic code wheel to detect a multi-turn, and you mount this motor on a ball screw, then you are absolute within this application. Something different are camera lenses, for example. We have also customer using the iC-MU and only a part of a magnetic code wheel to scan the focus and the zoom ring, for example. Or you can use it more related to robotics here, the electrical grippers, which are coming more and more on the market. There you need also a position feedback, and this is an example for linear absolute measurement. So that's all from my side from now. So now we will see how Patrick set up our evaluation kit in a live demo. So Patrick, please go ahead.
All right, thank you very much, Magnus. Yes, hello and welcome also from my side. My name is Patrick Stahl. I'm Sales Application Engineer at iC-Haus, and today I want to show you in a live demonstration how to set up iC-MU and configure and calibrate the system. And I will also give you a little bit of hints and tricks out of experience what you can do with our GUI software, for example. Okay, let's get started. I have a demo set up here that I just want to quickly talk through. So what we see here is basically we have the MU1M evaluation kit, which hosts the MU chip on the top here. This is then connected via a ribbon cable to this MU1D breakout board, which allows easy connection to all the signals of iC-MU. You can see, for example, here I've hooked up a scope to the incremental output. Then you also have the possibility to directly connect one of our BIS adapters. In this case, we're using MB5U adapter, which provides power to the setup and also provides the BIS connection. This is then connected via USB connection to our host PC, which is running the GUI software. Here see we have a motor, and on that motor we have mounted the MU2S code disk. This code disk is also part of the MU1M evaluation kit. And you can see this MU1M is mounted here on a mechanical fixture, and this fixture allows me to manipulate the chip to code disk position in all 3 axes. Okay, to get started now, I would just like to position the iC-MU relative to the code disk, and I just do this by hand now. So I push this forward, and just by eye do a really rough adjustment now. I tighten the screw, and I think that's fine for now. And I start the motor so that the code disk is turning now. Okay. And now I would like to switch to our screen here, which shows the GUI software. For this, I have to share the screen here. Okay, so hopefully you all should be able to see this now. All right, so this is our GUI software here, which basically allows you to connect to the IC and manipulate all these chip-specific parameters. Earlier on, Magnus already said there's some new things in this software, and I'll come to that later. So please note for now, we're using a beta version, an internal beta version of this software here now. And I'll talk to you or talk about later what is new in this software. Okay, so I will connect now to this chip. And you can see the system is now connected to the iC-MU chip. And here on this right-hand side, you see the automatic analog calibration sections, and you will notice there's some things different here, so I'll explain this later. For now, just please accept it as it is. And when I push this Acquire Data button here, what happens is that an analog calibration will be carried out, which is followed by a non-use calibration. So both analog and non-use calibration are done with one button press. This is also something that is new in that software. Okay, let's do this. I'll start the calibration run. So the system acquires basically the data now and then calculates the correction parameters, puts them back to the chip, and then does another measurement again to see how good the calibration was. So you can see now, basically, the system has selected some calibration parameters here. And on the right-hand side, you can see the residual errors in LSB. So this is what the algorithm would like to calibrate in a successive iteration of a calibration. So if I run it again, it would try to further reduce these errors. But if these residual errors are close enough to 0, we can leave it as it is. So values around 1 are perfectly fine. No need for a second run. And you will see here, we have quite a bit of a phase error in the system, a negative phase error. And this is the first tip I can give you. In a actual system like this with the actual code disk, the phase error is related to the chip to disk position in the radial direction. So I'm showing the error here in this direction. And this negative error that you're seeing here basically means that the chip is a bit too much to the inside of the code disk. What I can do now, I can use my manipulator here to move the chip a bit more to the outside. And if we do another calibration run now, you should see that these phase values here turn positive, which basically means we're a bit too much to the outside of the code disk. Okay, yes. So now we have positive values here. And I think for now we can leave it as it is. It's a bit more to the outside, but as Magnus already said, the analog calibration is there for correcting these errors so that the system can work without any issues, even if you have some mechanical misalignment. Not a problem at all. Okay, so now I would like to take a look at the no-news curve here on the setup. Magnus said earlier on, the no-news calibration in an iC-MU based system is needed so that the system can be absolute at all times. So this no-news calibration adjusts the master to no-news phase difference of the two tracks. And if this is well adjusted, that means if the system starts up, it can immediately figure out the absolute position because it can determine which current master period the system is in. And as you can see here on the screen, we have the green no-news curve, which is the calibrated value. And you have these light blue lines, which basically are the limits of your no-news reserve. So these light blue lines should never be crossed or exceeded, because in that system, in that case, you have an issue with your system. And we recommend that these in-range values here stay below 60%. So in our case here, this is the case, and the system is well calibrated. And the last step would be you just write your calibration parameters to your EEPROM here, and that means you're finished with the setup. And on the next startup of the chip, basically, the chip will be able to read all these parameters and is calibrated again. Okay. So let me change one thing again here. Earlier on, I said we're using an internal beta version of our GUI software. And the most important thing that is new in this software is that basically we implemented a new analog calibration algorithm, which is almost completely speed independent. That means you don't need constant speed anymore to do your analog calibration. It can even tolerate standstill. It can tolerate change of direction. So it's a very, very flexible algorithm. And this was a feedback from our user base that they wanted something more flexible and easier to use here. So we put a lot of effort in this and tried to make this work. Currently, the software is not available to the public, but we plan to release this in the course of November this year. And if you look at the screen here again, one thing you immediately see, this section is a bit different here. So we only have one button here that's called Acquire Data. And what this button does is basically it'll start the data acquisition. And then you have these checkboxes here. And these checkboxes determine what is then done with this data that has been acquired. So if you have selected the Adjust Analog, that means the system will use this data to do an analog calibration. If you have selected the Adjust SPO, this means the system will use the data to do the no-news calibration and adjust the SPO parameters. And then there's also the option to do this continuously. That means the calibration will keep running until you manually abort the system. And as I said earlier, you can see here I selected both analog and no-news calibration. That means both the calibrations are carried out successively at the same time. So first analog calibration, then a no-news calibration. Okay, what you can also do is you can deselect these here. And if they're both deselected, that will mean that the system will acquire the data, but it'll basically not use the data to do the calibration. It'll just do a measurement to determine the current analog errors and the no-news error that is present in the system. And this can be very useful. For example, like I can show you now, in conjunction with the continuous data acquisition here and these phase values here. I said earlier on these phase values indicate how well your chip to code disk position is in this radial direction if you have an actual code disk like this. And what I can do now basically, I can select here a rather short calibration time. So let's just use 1 second for now. And you can also see, maybe I bring that up again. Now we can immediately or directly enter a calibration time. This is also something that is new in this software. And now when I start the data acquisition and I reset this to 0, because we want to start from scratch here, because I want to see how well my alignment is of the chip to the code disk, you will basically see that here in the residual error window, if you look at the bottom here, the phase adjust values indicate there's some phase error, so there's a radial misalignment in that case. And what I can do now is I can turn a little bit here with my manipulator in the radial direction. I'm a bit too much to the outside because these values are positive, so I'm moving the chip a bit more to the inside, and you see these values get smaller and smaller, and maybe a little bit more, and a little bit. And this looks almost pretty good, so I can stop this now. And that way I found the optimal chip to code this position in the radial direction, so there's almost no phase error left. I'm well aware that basically what I've been doing here now can only be done on a lab setup. Obviously, if you have a PCB, you need to fix with some screws or something. This is not that easily possible. But for a laboratory setup, where you just experiment and you try to understand the chip and get familiar with it, it can be very, very useful. And let's do another calibration run now. And you should see, because I already, and I use a little bit higher time now, let's say 3 seconds, okay? And you should see now, because I already did a perfect alignment in the radial direction, that the phase error that is compensated for here should be pretty small. All right, so you see I hit it perfectly. So the phase error sits at 0. And this is, of course, very nice then. All right, another thing I want to show you here is the Nonius curve and what you can do with it. Nonius curve is a very valuable instrument in the setup of the system because you can spot some common system issues directly on the Nonius curve because they create some characteristic patterns. So the first thing you can see here immediately is that we have like a little disturbance here. We can call it tooth or something. If you see something like this, you know that the magnetization of your code disk is not perfect at that point. This is the usual cause of this tooth. There's not much you can really do about this, and to some extent, I have to say this is normal. But if it gets too bad, you should maybe talk to your supplier of the code disk and see if they can improve the magnetization to eliminate this error here. Another thing that you can spot on the Nonius curve is if you have noise in your system. So to show you what I'll do now, I'll just increase the air gap a little bit here. And now I'll do another calibration run here. By the way, we have also the option here to start the calibration run in the Nonius calibration windows, and it has exactly the same function as on the analog tab. No difference. So if I do another calibration run here, you should see that the Nonius curve changes a little bit. And in that case, basically, you see it gets much wider, so much thicker. And if you see something like this, you know, okay, there's noise in the system, and usually this is due to your chip to code disk distance being a little bit too high. Because what happens is the magnetic field strength will be lower. That means the amplification has to be increased in the chip, which then will cause more noise in the system. Okay, so I can turn this back to a more reasonable distance now. And if I do another calibration run, you should see that the curve gets much thinner again, indicating you have less noise in the system. And this is what you want, because you can also see then you get a bit better of a phase reserve here if the curve is thinner. And another thing I would like to show you that you can see on the Nonius curve if you have like an insufficient analog calibration, or you forgot to do the analog calibration at all. So that means you have a lot of residual analog error on the system. This will create some characteristic patterns on this Nonius curve. To simulate this, I will go to the analog tab here. and the system has been calibrated. And what I do now, I just artificially introduce some phase error here. So let's say 3 degrees, which of course is here a value, you know, that is nonsense in this setup because it already has been calibrated. So I deliberately introduce a phase error now. And if I switch back to this tab, and what I do now is I just do a measurement of the data. I don't want to calibrate, I just want to measure and look at my no-news curve now. You immediately see this change tremendously. So you have this repetitive spiky pattern on this curve. And if you see a pattern like this, please keep in mind there's something wrong, most likely with your analog calibration. There's analog error left in your system, and you should have a look at your analog calibration again. Try to minimize this in that case. Okay, so this is what I wanted to show you now for the no-news curve. Another thing I would like to show is earlier on I said this new algorithm is pretty much speed independent. And what I can do now, of course, to demonstrate you is I can stop this motor here. So motor is not running anymore. And now I'll just turn this motor by hand. Let's take a bit longer calibration time because obviously I'm a bit slower by hand to turn it. And I'll select to adjust the analog and the no-news again. And let's reset this here to start from scratch. And now I start my data acquisition and I just keep turning this here from hand. I turn it, so this is far from any constant motion or anything. Okay. All right, and we're done. You see system found the perfect calibration values again here, and phase is 0 because I already have a perfect alignment. And you see the residual errors are quite low, so this is very good. No second calibration run needed. Your no-news curve also looks very nice, and you're done with your calibration. It's as easy as that now with the new calibration algorithm. Let's try another thing. I can try to simulate a bit like a system that has a limited range of movement. So I'll just wiggle the code disk back and forth basically. Like for example, you could have in a system that has some end stops. And this principle also that I show you now also applies to linear system. It's pretty much the same for linear system as for a system where you just use a limited range of motion. So let's try this. I try this by hand and I try to hit the same spot on the code disk as good as possible. So I move back and forth and back and forth and back and forth. And I need to keep doing this also now during the measurement run. It will measure how well my calibration was. Okay, and you see the system has calibrated. It has not calibrated perfectly because when I move by hand, the issue is I don't have any mechanical end stops. So I need to hit the same section of the code disk all the time. And if this always changes a little bit, then you might need to have more iterations than that for this algorithm to settle. But as said, this is only a problem if I really do it roughly by hand. Yeah? Let's have another look at the no-news curve here. Okay, you see I've only used a very small section of the code disk, and only for that small section also the no-news calibration has been carried out. Okay, so this is what I wanted to show you in terms of the calibration of iC-MU. And there's one more thing I would like to show you, a feature of iC-MU that might not be that well known, and it's called counter position. So counter position allows you to output the absolute position of iC-MU via the incremental interface. So what happens is, if you start up the chip, it'll basically determine the absolute position, and then it outputs as many counts on the incremental interface until this absolute position is reached, and then it stays at the current position. And this is a feature that can be very useful if you have a motor controller or drive, for example, that can start up prior to starting up the iC-MU. And then you start up iC-MU and your motor controller can count the pulses, knows the absolute position, and from then can work incrementally, decrementing and incrementing this absolute position. So let me try to show this here on the setup. What I'll use for this is a little picoscope setup that I have connected to this computer here. You saw earlier on the probes that I have here on the AB channel of iC-MU. And okay, the scope is running now. Let's move over here, and I'll disconnect the setup now, or let's connect it again. Just want to select a rather low position so that you don't get too many counts here, hopefully. And I stop the data reading. On the ABZ output, I just selected 4096 here, so quite a low resolution to not get too many pulses here. Okay, and what I do now, I switch off the IC, so I disconnect the adapter, which also disconnects power to the system. And let me set the trigger here, a single shot, and then I power up the system, and you see what happened here. So the system powered up, and then it output the current position as pulses here, and once it reached the current position, it stopped, and it stays at the current position. Okay, so that was all for the live demonstration today. I hope it was interesting to you, and maybe you could learn a few new things and get a few ideas from me. And yeah, thank you very much. And I hand over to Magnus again, who has a few more slides for you.
Yeah, thank you, Patrick. Very useful tips and tricks. Thanks.
Yes.
Okay, good. So presentation is working. Yeah. So I promised I have a last slide for you regarding magnetic code reels and linear tapes. So what you can see here, we have some of these magnetic code reels and tapes in stock to provide you some samples for the first mock-up sample to getting a really easy start in the laboratory. So we have axial and radial magnetic code reels in different diameters for the iC-MU available. We have also an injection molded magnet, the MU18S available, which is our design, and we provide it also in series quantity, the same as for the MU150 and the MU28S. And besides this, whenever you need higher quantities for series production, or you need a customization of such a magnet, we will provide you the information of the manufacturers of these magnets, so you can get in contact with them and discuss your application, your dimension, and your needs. So please write us an email and we will give you the contact information. Yeah, linear targets, I talked already about it. So I'm the end of our presentation, and before we start with the Q&A session, we made a little polling, so we like to get some feedback from you. So we may push out this polling now, and the question is, what topics would interest you most for an upcoming iC-MU series webinar or video? So are you interested in linear systems, or more in the calibration configuration, or multi-trans systems, so together with the iC-PBL, how this works, or 3-track no-new systems? I talked about a little bit about it to expand the measurement range or the diameters. So please take your time to vote. So thanks for voting. Maybe we can show you also the results of these. Oh, I can see calibration, configuration, and multi-trans systems are at position 1 and 2. So yeah, thanks for the feedback. And now I hand over to Henrik and starting the Q&A session.
Thank you, Magnus. Thank you, Patrick. Very interesting presentations. Really appreciate it, you taking the time here. And thank you for the audience here for placing a lot of questions. We will take the time to go through these. And if we run over time, we will record this. So you will see also this when you get it after the sessions have been concluded in your link. So the first question for you, Patrick, is if the target pitch does not match perfectly, what maximum phase error can be tolerated?
Okay, very good question. So basically, there's a difference in between MU and MU150 and MU200. For the MU, we can have a maximum phase correction values of about 6 degrees. And for MU150 and MU200, it's twice as much at around 12 degrees. So this is what we can equalize for. Usually we recommend to our customers that for the MU series, we do not vary more than 5% from the nominal pitch. And for the MU150 and MU200 systems, not more than 10%. This can be done also if you would like to have a little special diameter that you maybe cannot reach with the standard pitch. Then you can modify this slightly within these limits, maybe to get 1 or 2 millimeter more in a diameter. So it's perfectly fine. The analog calibration will equalize these errors and will not have a negative impact on the system.
Thank you, Patrick. I have another one for you here. So, does the automatic calibration process depend on the rotational speed of the pole ring? What are the required rotation speeds for the calibration process? Are there any minimum or maximum limitations of the speed?
With the new algorithm, it's very, very flexible in terms of the rotation speed. From very slow to very fast, it's possible. A bit of a limitation is that we would like to see a certain number of samples per magnetic period. So typically for the new algorithm, we would like to see at least 128 samples per magnetic period, a bit more. And then obviously your maximum speed is a bit limited by this because you cannot sample with your BIS interface, for example, indefinitely fast. So you basically have to do your calculation based on your speeds and your sampling rates, sampling time, or what the RPMs are that you can use.
Thank you, Patrick. So now we'll switch to Magnus. I have one for you. Is the EEPROM internal on the iC-MU, or do I need an external EEPROM on my hardware?
Yeah. The EEPROM is not internal, so you will need an external EEPROM. This is due to most of our chips having this, but the size of the EEPROM can be very small, 1K, 2K, it's enough.
Okay, then I have a follow-up question for you here. Is there a possibility to store an absolute calibration in form of a lookup table on the EEPROM as well?
Good question, yeah. So you can use the EEPROM for storing additional data. So you can also connect EEPROMs with 16K memory size. And then you have a user space where you can store some data which you may use from a microcontroller to build up a lookup table or something else. Or
okay.
motor data sheets.
Okay, thank you. Thank you, Magnus. Patrick, I have another one for you here.
Yes.
You said that the phase adjust can be corrected with the software. Why is it better to reduce the phase adjust to 0?
As I said earlier on, this is not really needed to adjust it to 0 because the analog calibration, the purpose of the analog calibration is to eliminate these errors. Of course, what you would like to avoid is that, for example, you have a phase error, let's say, of already 3 and 4 degrees, which might still be able to be compensated, but then you have some mechanical play in your system. And if you do a series production and you want to calibrate all the systems, you don't want to be in a situation where you hit basically the limits of the range that can be calibrated, so the 6 degree, for example. So it's always a better idea to put the phase error as good as possible, of course, in your mechanical setup. 1 degree, 2 degrees, okay, and then do the analog calibration, but don't put it like at a 5 degree, because then you might have some system that due to the mechanical alignment will not be able to compensate the phase for, because you might get at 7 or 8 degree. Yeah? But as I said, the analog calibration is exactly the purpose. You want to compensate these alignment errors when you put together your encoder device.
Okay, thank you very much, Patrick. Now back to Magnus. Can you tell us a bit about external influences like temperature or external magnetic fields? How big is the influence and what possibilities do we have to adjust for it or to make sure that we reduce them?
Yeah. Okay, then let's start with temperature. So when you have temperature in your system, of course, motors will getting warm and maybe starts from cold environment. a magnet, when it's getting warm, the magnetic field strength decreases. And so we need a higher amplification of the Hall sensor signals. And this is where I explained the two amplification stages. So we have a coarse and a fine gain, and this is automatic controlled. And we're doing a sine square plus cosine square to get always the same value within the chip. And so this automatic gain control will compensate temperature drifts. And what was the second one?
Yeah, what can you do to reduce it, to kind of reduce the influence from external magnetic fields? Sorry.
Yeah. External magnetic fields, for example, a brake or a motor has also some magnetic fields. I explained we have a Hall sensor array, and this means we have several Hall sensors scanning the magnetic track, the master track, for example, and then we have several Hall sensors to scan P sine, N sine, P cosine, N cosine, and we do a differential of this. So we call it's a differential scanning. And when you have a magnetic field from external, maybe a big brake or something, then you have the magnetic field of all sensors in one direction. And due to this subtraction of P sinus minus N sinus, for example, we can eliminate this constant magnetic external fields.
Okay, thank you very much, Magnus. So back to Patrick. How much movement is necessary to determine the exact position after startup?
I'm not sure I quite understand that. You mean the movement that is necessary to determine the best alignment of the chip to the code disk?
That's the way I read it, yes?
Okay, well, it really depends on how fast you can move it. Usually, I mean, if you put together an encoder, what you will do is you do some construction work, some mechanical construction work, and put all your tolerances into consideration, and then you come up with a device that usually you put over the code disk, and then it should be very well aligned. And the residual error, because there cannot be perfect alignment, then is compensated by the analog and the no-news calibration. So yeah, I don't know if there's a speed that you come to the correct position. Yeah.
Okay, thank you, Patrick. Now, next question back to you, Magnus. Here, is there a version for automotive application, and which IC level can be reached?
Yeah, so we have a qualification for automotive for the iC-MU 200. So it's ACQ 100 qualified, and it's grade 1, so with 125 degrees.
Okay, thank you, Magnus. So back to Patrick. What is the smallest number of turns to perform rotary calibration?
Well, the absolute minimum number is you want to record one full rotation. So in general, you always want to record the portion of the code disk that you will use later on in your application. And in a rotary system, obviously, we want to see 360-degree mechanical of the code disk. And usually we recommend to have a bit more than that, maybe 2 or 3 rotations, but this is enough then for doing a good calibration. And obviously, if you have a system that doesn't have the full 360 degree, like a linear system, or you just use a partial section of the code disk, then it's pretty much the same, and we want to see that range at least one time, but it's better to have it several times to be able to do a better averaging of the values. This always helps.
Okay, thank you very much, Patrick. And I have another one for you as well. So about the feature that you presented, the AB counts at startup, what would be happening if the motor is spinning? Would it create additional pulses added to the current position? Or is it necessary to start the motor at still?
The usual use case is that a motor would be started at standstill, but it would also work if the motor is turning, because the output pulses can be output basically very fast with the maximum frequency of the AB interface. You can select this edge distance. It basically also depends a little bit on what your counter on the other end of the system can do, how fast it can be. but usually when you start up the system, at some point it gets the absolute position, and it can really, with the highest frequency possible, output these edges, and then stay at the current position and keep counting from there.
Okay,
Yes.
excellent. Thank you, Patrick. I have another one for you as well. So your section got a lot of questions, which is great. So what is the optimal air gap for an iC-MU chip?
Yes.
For 1.28 millimeter / 2 millimeter pole pitch?
Yes, a very good question. We have an application note that you can also find on our website, and there we give recommended air gaps for the systems. For an MU system, for example, we recommend a nominal air gap of around 0.4 millimeters, and then we would vary that by about 0.2 millimeters. So it is always a bit better for MU, for example, to have a little bit of a smaller air gap, because as I showed earlier on, it'll introduce less noise. For an MU150 and an MU200, the air gap can be a bit larger, because the bigger your magnetic pole pitch gets, the bigger your air gap can get. For MU150, I think it's a nominal 0.5 millimeter, and for MU200, we recommend around 0.6 millimeters. But as said, there's an application note on our website that gives you these values, so have a look at that if you're interested in this.
Okay, thank you, Patrick. I'll move back to Magnus again.
Oh, good.
So is it recommended to use iC-MU in a highly magnetic environment?
Okay, yeah, this depends, of course, what highly magnetic environment means. Yeah. For example, when you are at the end of a motor shaft, then there is some magnetic fields, and it is made for this, so it worked in this environment. We had also some applications, for example, where it breaks at the end of a motor and it works, but then, for example, a customer has 3 different sizes of motors. The 2 bigger works and the smaller not. And then we came up that the shaft is with ferritic steel and the magnetic fields is in a bad position, and then he changed the material and then the system works. So it's always depending on what you are doing, but of course I would say yes.
Okay, thank you, Magnus. So Patrick, back to you. Regarding calibration, is it always recommended to do multiple runs, or could one read out in the range values via DLL and stop as soon as they are at 60% or greater than 60%?
As I explained earlier on, it's not always necessary to do multiple runs. You see, and for the analog calibration, you basically see your residual error. And the residual error, we recommend that to be as close to 0 as possible. So if they're at a value of 1 or maybe even 2, you can think about just stopping the calibration at that point. And once the analog calibration is done, and the values are reasonable and good, then also the non-use calibration can be done. So it also depends a bit on how much you want to achieve in your system in terms also of the accuracy. You could of course do multiple runs if you want to get the residual error as small as possible. And I think you have to get a feeling for that also in your system. To do measurements and see, well, okay, if I have a residual error of, for example, a phase of 2 LSB, I don't really see a degradation in the absolute accuracy of the system anymore, so I can stop at that point. So we always don't, especially with the new algorithm now, we don't recommend that anymore. With the older algorithm, you will see it takes usually multiple iterations, usually up to 3 iterations, until the residual error settled and got close enough to values of 0.
Okay, excellent. Thank you, Patrick. Yes. So back to Magnus. Is it or will it be possible to integrate iC-MU and PVL into one chip in the future?
Yes, I think there was some possibilities. The challenge is then the PVL is a battery chip which can operate from a battery with a really low current consumption. Of course it is possible, but sometimes we think about if it makes sense. So give us a feedback if this is necessary for you, because when we integrate it, the price of the iC-MU maybe increase a bit, and then for other applications where you don't need battery multi-turn systems, then you have this part inside and you must pay for it. So please give us a feedback, and then we can think about this.
Okay, excellent. Thank you, Magnus. So back to Patrick. Is it now possible to calibrate a linear system with variable speed and only one motion in a certain direction?
Yes. So a simple answer with a new algorithm, yes, it's possible. You can have one run in one direction, but usually what you want to do is you basically have one in one direction, and then you do another run just to measure the data again and to see if your calibration was good. So you always want to verify what the residual error is. But yes, I mean, basically with a back and forth motion, you could do all the calibration in a linear system. And as I said earlier, the new calibration doesn't require any constant speed or constant direction of movement for this anymore. You can even have periods of standstill, and the algorithm will still tolerate this.
Okay, thank you, Patrick. We have many more questions, so we'll keep going. The next question is, when will the new calibration library be available? Not the GUI. When will it be officially released for our customers?
Yes. So I said earlier on, we plan to release it by November, or in the course of November this year, and that means for both the GUI and the DLL. Of course, it's always possible if we have one customer here online that says, or several customers that says, I want to try it now. You can get in contact with us and we can see if we can give you a beta version that might still have issues and bugs. But as long as you're aware of that and are willing to test it, how well it works in your application, let us know, and we can see what we can give you in advance.
Okay, thank you, Patrick. We have a lot of calibration questions, so back to you again, Patrick.
Okay.
If the analog calibration is successful and the values are now within allowed specs, but the no-news calibration is not within limits, what can be done to correct it?
If you have a good analog calibration and you're within your limits and the analog is adjusted and the no-news is not within the limits and you cannot get it in the limits even if you do several runs, this usually means that you have an issue also with your code disk. So you might have a bad magnetization of your code disk. Sometimes you might have eccentricity in the system for a rotary system that is so bad that the SPO parameters cannot equalize this eccentricity in the system again. Then you need to have a second look at this, because one thing is for sure, MU system needs a good no-news calibration. So if you have a bad no-news reserve, that means once you calibrated the system and you have later on some mechanical movement in your system, the system sooner or later will fail, because with a low no-news reserve, there's not much headroom for any more mechanical chip-to-code disk movement. So it's very important to get this right.
Okay, excellent, Patrick. I think I have one for you now, Magnus.
Oh, okay, good. Thank
so, what is the temperature range and the shock vibration limit up to which the system can operate safely?
Yeah. So for the temperature range, it is so the chip itself, it's designed from -40 up to 125 degree. But due to some thermal things, and you need to get out the heat of the chip to the PCB, the ambient temperature range is plus 110 degree for the MU and MU 150. And for the MU 200, also due to the bigger package, we have increased this ambient temperature to 125, also to reach the automotive qualification. Then. Yeah.
Excellent. Thank you, Magnus. So back to Patrick. No pause for you here. We have a next question regarding the new calibration algorithm. Can it run both on SPI and BIS interfaces?
Yes. Simple answer, yes.
Simple answer, quick answer. Thank you very much. And was the new calibration functionality tested with some custom pole rings with smaller or bigger pole pitches?
You mean that do not have the nominal pitch? I think, good question, but I think our software team did some tests with this. also with different misalignments and all this. We did extensive testing on this algorithm. But if you have some points that you would like us to check, I mean, either let us know, or as I said earlier on, we can offer to see if we can give you a beta version, and you can do some tests on your own and see if you see any issues at that point. As I said, it's still a beta version, so until the final release, we still have opportunity to do some adjustment if this is needed.
Okay. Thank you very much. There are still a couple of questions that have come into us, but we are running quite much over time, and we really appreciate your questions. Just rest assured that we will answer your questions by email. We have got your questions, so we know where to answer them. And thank you very much. It's been very interesting for us to hear your questions, your interest in how to set up the calibration and the features of the iC-MU series. So we really appreciate you asking these excellent questions. So that concludes today's session. We would really like to thank you for attending today, and I also want to thank the co-presenters here, Magnus Meyer and Patrick Stahl, for an excellent presentation. Thank you.
Yeah. Thank you for all the attendees.
Thank you.